Hi. As you see, we start with a new chapter. The first chapter was on logic. And logic, of course, is a very important part of mathematics. And in fact, when we do mathematics, we use logic all the time. And the other thing that is extremely basic is what mathematicians call foundational, is the notion of a set. And therefore we're going to talk a little bit about these so-called basic structures of sets, and then a bit later on we'll talk about functions. Because almost everything that I should not even say almost, everything that we do is somehow a set or the elements of a set. So what is a set? Well, okay, I guess we kind of know what a set is. It's a kind of I cannot really give a rigorous definition in the sense that it's so basic that we have to, it's one of the building blocks of mathematics. It's a concept that cannot be defined using other concepts. That's why what we call foundational. And so what is a set is a collection, and what is a collection of objects, and these objects are called elements. So very often a set is written in a capital letter, and then its elements are written in small letters. So there are different ways of saying that an element, so this is an element. So element is the mathematical rigorous term for an object, a member of a set. So this is a set. And one way to denote this is this symbol. It looks a bit like an epsilon, but it is not really. It's like, it has its own symbol. And we read it, A lies in A, or A in A, or A is little a is a member of big A, and so on and so forth. Okay, so that's a set. Now, a couple of things I should say, a bit more precise what a set is. A set is a collection of objects, but it is unordered. So the order in which we list this object is not important. So very often, so how can we, how can you represent sets? There are many ways of representing sets, and we will discuss a few. The first way is by just saying it's a collection, like capital A, without saying much more about it. But of course, more often than not, we want to actually make it more explicit what these elements are. And the first simplest way is to enumerate the elements in the set. So for instance, I could say a set V consists of the numbers 0, 3, 7, and 13, say. Now, you might say, so is there a rule? Is there like a pattern? No, there doesn't have to be any pattern. It could be any collection. In fact, here's another set, could be 0 and the letter A, and then a house could be in there. Okay, I'm very bad at drawing. And then a person could be in there. So I'm drawing this, but I mean to say, I really put in the set a certain person. There could also be a social security number in there. This is not a social security number, but let's pretend it's something like that. So it could really be a collection of various objects, and these objects have nothing to do with each other necessarily. Okay? Another thing that can happen, and very often happens, is, here is another one. So I'm going to call them V, each time V. These are different V's, of course, right? So another V would be, a set. Let's say it contains 0, and it also contains the set containing 0 and 1, and perhaps it contains another set that contains itself a set. So it gets a little bit tricky, right? So let's see whether we have nested everything correctly. So we have these two are together, and then these two are together, and then we have perhaps a different color. These two form a set. So you see, a set can be sitting inside another set as a member, as an element. So the distinction between element and set is somehow a little bit vague, because elements can be sets. But not every element is a set. In some, I should be a little bit careful to say that, because there is a way of defining mathematics where everything is a set. Okay, but for us, 0 and 3 we don't consider them sets. But there is, as I said, if you would look into a very rigorous book on foundations of mathematics, you will see that 3 is a set containing a very weird set. 0 would be the set that is empty. So, well, now that I brought it in, perhaps a very special set is the set that is denoted by a 0 with a stripe too. But it's different than a 0 than we would normally. Don't confuse it with this, which is often a way of denoting 0 to making distinguishing with 0 and O. But this is the strike goes all the way through. It's almost like a Greek letter phi, but it is slanted. Okay, you see in the textbook also better how it's printed. And so this is the empty set. What does that mean? Well, empty means that there's nothing there, right? So this is a set that has no elements in it. So, and it has a special name. So this is the name of that set. It's not a symbol that I just invented. We're always going to use this symbol for the set. That's an empty set. Now, how can we enumerate them? Can we use the enumeration technique? So remember, you see that I perhaps should have said this. It starts and it ends with these braces, right? Always. Okay. So it starts with a brace and it has to end with a brace, and then in between is everything that is an element. But there is nothing. So that's how we would write it. Okay, don't put anything there, because the moment you put something there, even a dot, now it becomes a set containing that dot. Okay, so it really has to be empty. That's what empty is, right? And by the way, it's the fact that something is empty is somehow a little bit counterintuitive to people. People tend to not want to see the emptiness. Emptiness is something that we actually never can really obtain. Okay, you see that when you walk in the plains and you say, oh, it's so empty here, but of course it's not empty. Or even if you go into space and you say, oh, it's so empty here, there's no air here, but it's not really empty because there are particles there that you cannot see. So emptiness, empty space, vacuum, but true vacuum is almost impossible to attain. Yet, as a mathematician, we very often use the empty set. That's why it has a name. And things don't, in mathematics, things get a name if they are used a lot. Otherwise, they don't get names. So empty sets are very important, and you'll see how we constantly will use them. Okay, that's an empty set. Then that's a set with 0 elements. Okay, so what's the next thing is we could take a set with 1 element. So this is a set with 1 element, for instance, the letter A, or it could be the element, could be a set itself. Say capital A, so where capital A is some set, or it could be as like, look, I can do this one, right? That would be a set with a 1 element in it that itself is a set with 1 element in it. Now, what we call these sets with 1 element, so 1 element sets. Sorry, let me write it this way. So a 1 element set also has a name. It's less important, but I want you to know, I want you to hear it at least. It's not, we're not gonna, you don't need to know it. It's singleton, single meaning alone, okay? So I want to point out again here with this thing, this guy here is a set that is a singleton containing just 1 element, namely the 0. So what about the bigger set? This set here, this whole thing, is that a singleton? Yes, because it contains 1 element, namely that set, that particular singleton. Okay, it gets perhaps a little bit, you have to keep your head straight a little bit there, and it's somehow a little bit, if you do programming, and so you might have encountered this also, these are types, right? And it's nested types can happen a lot in programming, and this is also what we have here. Now, sometimes sets are a little bit too big to just all numerate them everything. So for instance, if I want to enumerate the first 100 numbers, that's going to take me a long time, and therefore I put the 3 dots, ellipsis this is called, and then I put the last number that I want, 99. This, in some sense, is a little bit inaccurate because the ... is not exactly telling me what is there, but it's often used only when it's so obvious to everybody what it should be. And so, in other words, let's figure out. We can look at, is the following, I'm going to write a couple of things and ask whether they are in there. Is the letter A in there? Is the letter 4? Is the number 4 in there? Is the number 104 in there? What about A? Is A in there? Question mark? No. Because These are supposed to be the numbers 0, 1, 2, 3, all the way up to 99, and A is not such a number. 4 is in there, yes, so we have this. What about 104? No, 4 is not, note that I didn't list 4, but I know that the dots imply that 4 is there. Okay, you get what I mean? And then 104, no, because the fact that I write 99 at the end means there's nothing beyond that anymore. Now, I could, for instance, another way, even harder to deal with, is things that are infinite. So I could write this here, and now I didn't put anything on the end, which means it goes on forever. So in this case, 104 would be in there, because I have not said that there's an end to it, okay? And these, of course, as you see, these are so-called natural numbers. Now, they are so important also, they often occur a lot, especially in discrete mathematics, that we have a special symbol for them. So we denote this set, so let me put this in front here, that you... So we have given name to this set, we call it N. Now, in the book, they use boldface, but more often than not, mathematicians use this kind of typeface that is a bit weird, but we call it blackboard bold. I don't know. But so you will always see me write it this way. And so I will only use this for the sets of numbers. So, and there are, of course, other sets. Let's look at this one. What do I mean, this one? So these were the natural numbers. These are the integers. What is the difference? Well, they're also negative numbers. So we have 1, 2, 3, but we also have -1, -2. So this goes on forever there, but it also goes on forever there. You see, I have to sometimes be, and of course I have to always close it here, a little bit, I have to be inventive sometimes to write down something that is infinite in both ways. It could be infinite in many more directions, and now I'm getting a little bit in problem. So we'll discuss that later, what we do. So that's the integers. Now you might say, why don't, n for natural number, understand z for integer. Unfortunately, this is this comes from German. German mathematicians first started introducing this. Set theory, the father of set theory, so I should perhaps mention that. So the father of set theory, I'm not meaning to say that mathematicians didn't know what sets were before that, but he was the one that really developed it. The father, of course, between quotes, of set theory is a German called Cantor. And there's a little blurb on Cantor in the book. So, and that's, the Z is for German Zahl. It's one thing is it's written this way, Zahl, which means number, and it's pronounced Zahl. Germans pronounce Z's as Zus. What can you do? Okay, then another one is that we often work with is Q, and this stands now for fractions of quotients. Okay, this makes more sense, right? So we are now dealing with numbers of the form 2/3, 1/5, 1/5, minus 10 over 231, ... Notice that I have said something all the way in the beginning, and I should say this, perhaps I write it down here. An important property of a set is that it is unordered. We do not consider an order, yet so far I seem to be ordering everything except for my last time, and that is, I'm allowed to do that. Now, the ... is less clear here. What do I mean here? 2/3, 1/5, minus 10 over 230, ... Do I mean all fractions, or do I mean some more fractions that I'm too lazy to write down? Perhaps infinitely many, so I cannot write them down, but not all fractions. So you see, sometimes we need more, a better notation. And so another notation is descriptive, where we say, what is in there? Well, all fractions a, b, and then we make this line here. We say, what are a and b? A and b are integers. Now we know that b should not be 0 because that's the big commandment, right? Thou shalt not divide by 0. Okay, so that's a way to say. So notice that this is kind of a statement. More precisely, it's a predicate involving, in this case, two variables. And what we're saying is a and b. And what we're saying is that it's all, so what is at this side, let me perhaps use a pointer here. What is at this side here is the description of all possibilities that are this side of that dividing line. Okay, so that is a way of writing down a set more accurately. Now there is no doubt this dot dot dot, I don't know, was 5/100ths, was it a 5/3, was it in there or not? I might have thought, no, 5/3 is not there because all the fractions you show me so far are less than 1 in absolute value, or even less than 1. 5/3 is bigger than 1. So you might say, oh no, it's not in there. No, it's in there because here 5/3, take A5, B3, and you have 5/3 in there. Okay. Two more, the reals. So A, where A is a real number. Now here I'm kind of cheating a little bit. I'm defining a set by just saying it's a real number. So I have to actually say what the real number is, but that's not, this course is not about real numbers, so I'm not gonna make that more precise than that. But you see, again, a predicate, A is a real number that defines A. And so I can also then have C, that's the last of all. Can you get what that is? Complex numbers. And so these are all the numbers of the form A plus BI. I is the imaginary, the square root of, so I is, we always say, the square root of -1. I put it between quotes because a square root there are two square roots. There's one and the negative of that. Which one do we mean? The positive one, you say, yeah, but there is no positive in complex numbers. Complex numbers don't have an order relation. You cannot say what is bigger or what is smaller. For real numbers, you can do that. For all the numbers so far up to here, they have an order. By the way, this order doesn't play in the set, right? We set that. That's why, and this here you see C is unordered just by itself. It cannot be ordered. So, but we definitely want a set here. Now I have to complete this a little bit. A and B are real numbers, and they could be any real numbers. Okay. So, and so more generally, therefore, what we have, if we have a predicate, let's do P is a predicate, X, a predicate over a certain universe, then I can call all the x's such that Px holds. Well, let me put it PA such that P, okay, sorry. I'll use a different letter here so that you understand what happens. So we have a predicate with x is the variable, and now I put in all a's so that PA is true. Holds true, equal to 1. Okay? So, and this defines a set, and that's the set defined by P. So this is the set defined by P. Now, sometimes I need to be a bit more specific, namely I have to say, what is the domain of, remember, a predicate is actually always not just an expression, but also it has implicit somehow, very often we don't spell it out, but it means that the variable ranges over certain universe, can take certain values. And what values it can take? Well, exactly value. What does it mean, a universe or a certain values? It means it's values in a certain set. So for instance, I could write down the following set here. Let's look at all the natural numbers, m, such that 0 is less than m and is less than 10, or m squared is bigger than 1000. I'm just writing down a very weird set, but why not? And you see here, this is a predicate. So the predicate here would be P of x, if I want to spell out the variable. 0 is less than x is less than 10, or x squared is bigger than 1000. And now I have to be clear, if I write it down like this and don't say anything else, if you just see this and you didn't hear me say it, then you say, okay, I still don't know exactly whether, for instance, 9/2 is in there. Because 9/2 is between 0 and 10, so it satisfies the left-hand side, and that's enough for an OR. But I don't know whether m is allowed to be a fraction. And so that's why I have to be here more precise. I said natural number, right? So let's write it down. So m is an element from the natural numbers. So here we kind of make very explicit what the domain is for this predicate. Okay? And so we can define sets this way in many, many ways. And sometimes it's called a set builder, this P. We build a set or we define a set by a predicate P. Now, okay, a couple of things. So when A is equal to B, so A and B are sets, if and only if, this means, or this holds, If and only if. Remember, this means if they are equal, then what I'm going to say is true, and what I'm going to say means that they are equal, namely if they have the same elements. You might say, Professor, this is what I would call a tautology. This, you're saying nothing. Of course, two things are equal if they have the same elements. Okay, so here, what do you think? Are these two sets the same? Answer, yes, because order is not important. Are these two sets the same? I'm going to use the same one here, and I say, no, they are not the same, clearly not. No, they are the same, because they have the same elements. What are the elements? 3, 1, and 5. Just because I like to write them several times doesn't mean that they are there several times. An element is there or it is not there, right? It's only yes or no. Not it's a 3 there, 3 times in there, that's not it. By the way, there is a notion where you actually count how many times a number is in there, and that is called sometimes a multiset or other names. But when we say set, we don't mean this. So this is equal, because these two sets have the same elements, namely the elements are 1, 3, and 5. And it doesn't matter in which order. I'm just saying that the elements, but what order is not important. Okay. Another important thing is another way of representing, and a very useful sometimes way, at least when you're dealing with not too many sets, and also with finite sets. Discrete math. What is discrete math? We haven't really defined really what this math is, and it's not really exactly possible to say what it is, but it talks about so-called discrete elements. What does that mean, discrete? What is discrete? The numbers, the natural numbers are discrete, for sure. Another thing that is discrete are, for instance, logical symbols, logical propositions. These are discrete objects. What is not discrete, for instance, is the real numbers. It's not considered to be discrete because between any two real numbers you have another real number. Discrete somehow means there are gaps. Now, granted, this means that we're thinking, when we talk about gap, we think there is an order. And I have said so before, there actually doesn't need to be an order. Okay? But very often there is. So, okay, so discrete is a little bit perhaps vague what it means, but very often you'll see most of the time we will dealing with either natural numbers, and much less in this course, but in discrete math 2 we'll see other objects like graphs, trees, and so on. That's also considered a discrete object. One feature that they have almost always in common is also that they are finite, and that makes a big distinction also, that we will deal with finite things. And therefore, for instance, we have now a set. So here's my set. Let's call this set A here. One way of representing this set is by so-called a Venn diagram. Again, Venn is not an English word, it's a name of a person. So a Venn diagram, that's something that sometimes they teach already in pre-K, right? Or I don't know about when you have seen this. And that means a Venn diagram basically divides the whole thing, the universe, in two parts, the outside and the inside. And the inside, we list our elements. You put a dot and then give the name to the element, 1, 3, and 5. And so, for instance, 2 and 4 would live here. Also, A would be there, letter A. And also that guy that was sitting in my set before, he's actually there, not inside the set. Okay? That's what we call a Venn diagram. Okay. And another important note, and we'll come back to Venn diagrams a bit more, but we need, okay, you have to be a little bit patient in this particular section. You'll see it's not that long, and also the homeworks are not difficult. What it is though, it's a lot of definitions. We are introducing new objects that we then later gonna play with, okay? So another thing that we have to talk about is a subset. So sub, underneath, sitting in this case it means it's a sub collection. So subset, so we say we have set A and we say A is a subset, and we notice like this. Let me try to make this a little bit more clear. It is like a C with an equal sign underneath. It's very much the same C where you put a bar like that. Be careful, it's not this, right? This is A is an element of. This means A is a subset of B. What does this mean? That means every element, every A in A, then A lies in B. I'll write it down a little bit cryptically, but you see what it means. Every element that is in A is also an element in B. Okay, so if this is A and this is B, let's call this 1, 2, 4, 5, 6. Is A a subset of B? No, because this element here is not contained in B. So here we have an example of, so in this case we have A is not a subset of B. So very often when we want to negate something, we just put a bar to the whole thing. Okay, so A is not a subset of B. Now, okay, what about, I'll introduce another guy here. Let me give me some space here. C is the little guy that we had before. Well, I don't know why he's little, but okay, he's there. And then also the letter A, 3, and then 100, and then also X, and also 1. And I also put in the letter A one more time because somehow I forgot that I put it there, and 3 again because I forgot I put it there, and 5, and that's it. So is A a subset of C? Yes, because every single element of A, 1, here is 1. 3, well, here is 3. It's there twice, but remember, it doesn't mean anything. It's just there once. It looks like it's there twice, but it's there once. 5, yes, 5 is here. So here in this case, so let me write it up, the conclusion, sorry, not A lies in C. Okay, that's the notion of subset. By the way, notice that A is equal to B even only if A is inside B and B is a subset of A. Think about this. But this is a true, but I want you to think about it. I'm not going to work it out. Okay, how do you see this on a Venn diagram? Well, here, let me do a little bit simpler here. So we have 1, 3, and 5, and let B now, a new B, be the set 1, 2, 3, 4, 5, 6. Okay, so here is B. B is 1, 2, 3, 4, 5, and 6. And notice that this is A. And I can draw A inside B. Of course, I could have made my loop a little bit bigger. I could have done this, right? I could draw it like this way, and then it looks like it's not in there. But this would, there's nothing in that part that sticks out would not contain anything anyway. So we can as well shorten it if you want. Notice that Venn diagrams are just visual representations, okay? And they're not unique by no means, right? Because you see, I'm not very good at drawing ovals. This is supposed to be an oval or an ellipse, or it could. And then you will see sometimes Venn diagrams can have weird shapes because otherwise it won't fit the pattern or something like that. So, okay, it basically is. You should think of it. This is the fence of a meadow, and then these are your cows that you want to keep inside your meadow, and these are the bulls that you don't want to mess with your cows. They're outside. Now, okay, these are outside of A, but of course they are inside and still B, and then there are things here. So for instance, 7 would be there. Okay? Okay, so a special subset, the empty set. That's always a subset. Let's think about this. You say, well, that doesn't make sense to me. Well, when are you a subset? If every element in the empty set is also an element in A. But every element in the empty set, it's what we call a vacuous statement. It's a statement. Remember, it's a statement where that doesn't apply to anything. So there is no element in phi. So the condition is satisfied. Remember, P then Q is true if P is false, and in this case, A is an element of phi is false. There is no A. So remember, I'm trying to prove this, right? I'm trying to do this, but now let's pick B here. Now replacing, so I'm going to replace my A here by phi and try to verify this inequality. Okay, let's do that. So I'm doing this here. I'll do it in a different color. So this is now, if A is an element of phi, then A lies in B. Is this a true statement? A, an element in phi, sorry, let me just perhaps not, let me write it up again. A, an element in in the empty set, I shouldn't say phi. If A is an element in an empty set, then A lies in B. Is this a true statement? What about the truth of this statement? This P, this is the P that I'll talk about, is false. Always, because there is no element in phi. So we have a falsity here that does, and therefore, no matter whether this is false or true, this statement is true. And that's the statement that guarantees the set inclusion. So you see that why we have to make P then Q to be true if P is false. If the moon is square, then I am as rich as Donald Trump. That's a true statement. Okay. Because the moon is not square. Not because I have a lot of money. Okay, next thing. We talked a little bit about the size of a set, and of course the size of a set is the number of elements. So the book writes it this way, with bars around the A, and so this is the number of elements. Okay, and what's the size of B here? B has well, A and B were listed here, right? So here is A and B. Oh no, that was a different B. Here is my A and B. So here, let me write it here. The size of B is the number of elements, 6. So be careful, right? Let me go back to an example that might have thrown you off a little bit, but here we go back to the example that I erased. Oh, I erased that example. So let me do the example again. What's the size of this set? Three, because there are only 3 elements. Some of them are listed several times, but there are only 3, namely 1, 3, and 5. Okay? So don't be fooled by this kind of visual misrepresentation. Okay. So perhaps I should also then, let's make the Venn diagram of this thing. What's the Venn diagram of this set A here? Well, in a Venn diagram, you should only put 1 dot for each element. So I should not repeat the elements in that Venn diagram. Okay, be very careful. It's very easy to do that if you don't pay attention, especially if there are more elements. So you have to be careful to not do that. I'm not saying it's fully wrong, but it is misleading. And while one allows this to happen in this set notation, normally when one wants to represent something in order to understand it better, you don't want to confuse anybody, so you don't want to do that. Okay? Okay, so that's sets. All of sets, as I said, will be finite, but sometimes sets are infinite, by the way. So, for instance, N is infinite set. It's an infinite set. And there's very easy and very nice things about infinity. You think, oh, so this is an infinite set and this is an infinite set. They're both infinite, right? That's it. No. They are both infinite sets, true. But there are different types of infinity. Unfortunately, this is not part of discrete math. It is in the textbook, so if you're interested to hear why this has a different size of infinity than this, by the way, what you think, which one you think is the bigger? The real numbers, right? There are much more real numbers. It seems like, okay? But if you want to see that, read in the chapter on cardinalities. So the number of elements is also sometimes called the cardinality. So we call this the cardinality. And unfortunately, I am so used to also write the cardinality with this sign here, with the pound sign, instead of the square bracket. So you might, the brackets, the right straight brackets, you might write this instead of that. I apologize, and it's just because that's actually a more common, or and as common, I shouldn't say more common, as common as the other one. I'm used to it that way. Okay, so about infinite sets, we're not going to talk about. By the way, Q is also an infinite set. Just to throw this into, what do you think? Do you think it's as infinite as this one, as infinite as that, or it's even somewhere in between? I'm not going to tell it to you. You have to read it yourself if you want to figure out what it is. Okay, so that's about sets. Now, and one last thing. No, I don't know. Is it the last thing? No. A couple more definitions. The power set. So we have a set A. So A is a set, and then we build a new set P of A. The power set of A. So the power set of a set A. Sorry. Okay, I'll repurpose my A here. So the power set of the set A, what is that? We denote it PA. That is all B such that B is a subset of A. So this is another way of saying B is the subsets of A. Somehow it seems important to not just talk about one subset, but about all of them, and that we call it the power set. Now you might be a little bit asking why power. Okay, let's look at the set A. I'm going to take a very simple set, otherwise I'm going to take too much time. A, 1, 3. What's the power set of this set? Okay, so now I have to list all the subsets. Now, don't forget that the empty set is always a subset. So that's the first subset. Then that's this set with no elements. So let's list them in the number of elements. Of course, there can never be more than 2 elements because A itself has only 2 elements. And I hope that, perhaps when we talk here about cardinalities here, I hope it is clear that this is always true, right? If A is a subset of B, then the cardinality of A is less than the cardinality of B, because every element in A is in B, but B could have more. B cannot have less, but it can have more. Okay, so the next possibility is the singletons, and there are 2 of them, namely 1 and 3. And that's it, you say. No, because A itself is also a subset. So I should perhaps also point that out here, that when we talk, we're a subset here. Note, A is a subset of itself. Why? Well, put here A and put here A, and that's a true statement. If A is in A, then A is in A. Yeah, right, that's true. Okay. So that's it. So how many elements had this? This had 2 elements, and this now has 4 elements. Okay, let's do perhaps one more. Let's go to our set that we have been using a couple of times. 1, 3, 5, 1. Let me fool you a little bit. Remember, the set has only 3 elements. This second 1 doesn't mean anything. So what is its power set? Well, there's going to be the empty set. Then there are going to be how many singletons? 4? 1, 2, 3, 4. No, 3. Because there are only 3 elements. Sorry, my braces are sometimes getting ugly. Now, there are sets with 2 elements here. Namely, I can take the 1 and 3. I can take 1 and 5. I can take 3 and 5. Let's think about it. Can you do more? No. There's the only 3 combinations with 2 elements that I can have. You say, what about 3 and 1 then? That's another one. No. Is that different? No, I have this already. These 2 are equal. Why? Because they have the same elements. Remember, the set is unordered. The order in which we list the objects is irrelevant. So if I write 3, 1, I am doubling something that I have already. So that's not correct. Oh, I have to get rid of this thing, and it is going to show me the calendar. This is so stupid. Oh no, it goes away. Okay. Okay, so is this it? Well, no. Remember, the set itself, that's the set with 3 elements. Remember, A has 3 elements, right? Is the set 1, 3, 5. That's going to be the last of all the possibilities. Okay, how many do I have? 1, 2, 3, 4, 5, 6, 7, 8. So we had 3 elements. Now the power set has 2 to the power 3 is 8. But why do you write 2 to the power 3, Professor? Because that's how it works. If A has n elements, then its power set has 2 to the n elements, a power of 2. That's why it's called power set. Okay. Last thing. Oh, here. Okay. I'm going to leave this for you to think about. What's the power set of the empty set? How many elements should it have? Well, let's see. If this formula is correct, then I can determine how many elements it has, because how many elements does the power set have? 0 elements. How many elements does the empty set have? 0 elements. So this should have how many? 2 to the power 0, 1 element. Which one? Well, the empty set itself. Remember, the empty set is always a subset. And also the whole set is always a subset, but in this case they're the same. That's why there's only 1. Okay, cute, huh? All right. So, last thing, I think it's one of the last things that I want to do. Yep. Yep, yeah. Let me. That's the only thing I need to do. Is a Cartesian product. Remember, I said sets have no order, but sometimes you do want to order things. And for the simplest way of ordering is looking at pairs. So, for instance, what is a pair? A pair of natural numbers. Pair of natural numbers. Let me write everything in caps. That's more legible for you guys, right? A pair of natural numbers. Suppose I want to write a pair. Well, we know, for instance, 0, 3 would be a pair of natural numbers, or 4, 6 would be a pair of natural numbers. By the way, it's also 7, 2 is a pair of natural numbers. I've not said that the first element has to be the smallest. A pair is just a first element, a second element. But the order is important because the pair 2, 7 is different from the pair 7, 2. Because remember, what could this be? This could be, for instance, coordinates, right? If these coordinates in the Cartesian, Cartesian, I haven't explained the name yet, but remember the Cartesian plane, the x and y axis. So if you think of these as points, so this point 7, 2 here, where does it lie? 1, 2, 3, 4, 5, 6, 7, 1, 2. So this would be this point. And what is the point 2, 7? That corresponds to 2, 3, 4, 5, 6, 7. That would be this point. Let me get rid of these two other guys here. Sorry, I'll do it again. So that would be this point here. So this is the point 2, 7, and this is the point 7, 2. Clearly different points because, of course, it's an ordered pair. The first coordinate is the x coordinate, the second is the y coordinate. If we wouldn't order them, we would not know what is what. Okay? So how do we represent this? Okay, pair of natural numbers, of course. In the Cartesian plane, you actually have pairs of real numbers. Coordinates can be real numbers. So, but the notation is n cross n. And so when we say n cross n, we mean these are the collection of all pairs A, B, with A and B in the natural numbers. Sorry, I get a little bit in the way here. Let me get rid of this. A, B in the natural numbers. But there is actually no reason why the first element has to come from the exact same set as the second element. Very often, for instance, if you are listed in my course grade, you're listed with your first name, your last name, and your student ID. So I have a pair of 3. Well, that's not a pair, that's a triple, sorry. Or let's say first and last name, okay? We have a first name and a last name. And suppose that first name I should list that first, although very often that we do the opposite in grade centers and so. But so we have a pair. Now both are names. Okay, that's true. But if I take a name, a first name, last name, and a social security number okay, sorry, I wanted to give an example with 2. We will come to triples right away, but just let's stick to the pairs. Let's say a last name and the student ID. That should identify you for sure. Okay, so that's a pair consists then of your last name would be Bensonian. I'm sure that's not a name, so I make that up. And his number and his student ID would be 1111110 in 11. So this is a name. This is a number that's of certain length. Okay, so very often we have pairs that come from different sets. So we want to make a general Cartesian product. So A and B are any set. So for instance, A could be the set of all names and B could be the set of all student IDs. And then what is AB? Well, that is the collection of all pairs AB where the first entry is from A and the second entry is from the set B. Okay, that's what we call a Cartesian product. And what is this? It's a set again. Okay, so we can do this for small things. So suppose we have 2 numbers and 2 letters and we take the Cartesian product. What are the possibilities? Well, the first element could be a 0 and the second element could be either an A or an E. The first element could be a 1 and the second element could be either an A or an E. It is all possibilities. Okay, I did 2 and 2 here, perhaps it's not so clear, but if you think a little bit about it, what do you think is the cardinality of a Cartesian product? The way I build it is I choose an element from A, and then I take the first element in A. Well, there is no first. I enumerate my elements in A and take the first in my enumeration, and then I list every element in B. That gives me all possible pairs with first entry, the first element I chose. And now I repeat this for the second element, and so on. If you think a little bit about it, the total number is A times B. Now, we will not talk about counting, really, this kind of counting principles and cardinalities. This is something from discrete math too. But this is a simple enough idea that I hope you understand how we calculate this. And you see it here, okay, both are 2 element sets, so the total has 4 elements. Okay, so these are the ordered pairs in short. Now, there is absolutely no reason that I would not look at triples. A, B, C would be all A, B, and C, where A would be in the first set, B would in the second set, and C would in the third set. Okay. Now, of course, I can have some of these sets to be the same, but I don't need to. Now, if I take both sets the same, so for instance A times A, then I call this a Cartesian. So these are called Cartesian products, right? Here's the name, Cartesian product. But if I take the same set, I sometimes want to express it by saying Cartesian power, because it's the same A. Okay, it's a power of A. Well, my power of A, look, if in this formula I take A and B to be the same, then this becomes a square, right? A power. Okay, that's another reason why we use the word power here. Cartesian power. And so, for instance, the very first example I gave, this was a Cartesian power. And this is then very often denoted as just A square, really as a as a power. So you would write n square here. So if we have a set squared, then we actually mean, not, what does that mean, to square a set? It really means it's the pairs with elements from that set. And now, of course, I can take A cube, that would be A times A times A. So this would be all triples of elements who all those entries lie in the set A. But I said we can make more general triples this way. And of course, it doesn't stop with 3. We can 4, 5, 6. We can do even infinite, but that, again, is not discrete math. So I'm not going to say much about that. Okay, I think this is everything I needed to say. Yeah. So one more last thing then. Why the name Cartesian? Did you ever know why we call about the Cartesian plane? Why we call it Cartesian? Well, it's named after a person whose name is not Cartesius or Cartesian. His name is Descartes. That doesn't sound the same, right? But first of all, if you write it, it comes out. It almost becomes the same, because in French you don't pronounce. French, they like to swallow a lot of things, so Descartes instead of Descartes. Okay, so okay, Cartesian is actually this part, and the de there is kind of like the or Mr. It's like in, remember Hopital's rule in calculus. It's actually de l'Hopital, so it's a little bit similar to that. So he was the first to describe this. To describe the plane using coordinates. And that was a very major breakthrough, because it brought geometry, planes, into the realm of algebra, where you do work with numbers. And so these two different objects, seemingly different objects, can be treated in the same way, because there's a connection. And that's, of course, what mathematics is all about, is making connections. Okay, so we have set up all the things that we need to discuss now a little bit more properties of sets and play a little bit with these sets. But more importantly, these sets will be the building blocks where everything else we will constantly use. Okay, I'll assign some homeworks, but you'll see the homeworks are not so difficult.